Good morning. So welcome back to text mining. Before we start, do you have any question for me at this time? Okay, so let's continue our topic today. So we're going to finish some unfinished business last time, which is to look at support vector machines, which is a supervised classifier, and that's used normally for binary classification. So you have two categories. You want to know whether a unseen input, which category an unseen input would belong to. And you have a training data. So the training data is classified into two groups. So we use plus, we usually use plus to indicate is a positive so for each data we use a plus to indicate it belongs to the positive class. The other one we use negative or minus to indicate that the input belongs to the negative class. So because it's a binary, so we can label these two classes any way we want, but using pluses and minuses are common. So last time we looked at two classifiers. One is lazy learners, which is a KNN. Lazy learner just means that you treat an unseen document as a query, and then we directly use text retrieval methods to return top K documents that are relevant to the unseen documents, and then the top K occurs from your training data. Because these training data for each document, it has a label. Then we simply do a majority vote to determine what label we should give to this unseen document. So that is KNN. So there isn't much learning to do. So the only thing you do is just to come up with a inverted indexing mechanism from forward index. So that is KNN. And of course, there are two variants. One is to add weight to each document, depending on its similarity with the unseen document. So you can add a weight. So the weight would be similarity, right? So it's more similar, then the weight should be bigger. And one of the common ways to do it is to multiply each document, use 1 over R to be a weight, and this R is the distance. Really, it's just a similarity. So another way to look at similarity. And we can also compute a centroid for each class, for each cluster, right? And then for an unseen document comes in, you compute its similarity between each centroid points, and then whichever is closest, you will pick that one and use that label. So that's KNN, lazy learner. And then we look at a language model based classifier that's called naive Bayes. So naive Bayes is to really try to compute the probability of a document, let's say X is an unseen document, Y is a label. So I want to know I want to know this probability. Okay, so, and then we know that it is equal to the so in other words, this actually we are going to look at features, right? So this is a feature vector. So this is a feature vectors. And because, so this feature vector will be, let's say, S1 up to xk. And then we assume, so naive Bayes has to make an assumption that these features are independent. So then you can, so this then will be equal to x1, so times x2 times xk. So then you really want to maximize this, and then so this is the product. So you take a log, then you then you have a summation of the log. Then you just try to maximize it. Whichever that's maximized, then you use that label. Then that y will be your label. Okay, so that's based on language model. And this naive Bayes is linear classifier. So in other words, it's basically, you have, let's say you have on this picture, you have, so let's look at these different shapes and different color things, features of certain documents. So they can be, in this case, they can be clearly classified into two clusters, and actually they can be separated by a line. So this is linear separation. So by the line means linear. Okay. So this is a linear separation. So on a two-dimensional space, you use 9. If on a high-dimensional space, you use a surface, use a plane, right? So on certain angle to separate these documents. So they are still linear, but it's on high-dimensional. So what we really want to do is to find, now if your data can be separated by a linear subspace, right? So two-dimensional, then the linear is a 9. So let's say they can be separated, but then there may be more than one such separations available. For instance, here we look at two 9 separations to separate these objects. So obviously, if you intuitively, right? So if you look at this 9 is a better separation because the margin, so from the closest point to this 9, or so this is called margin. So you draw the 9 that's a perpendicular to this linear space, then that is its margin. So it looks like the smallest margin is here. So this is obviously, the margin is bigger than this, right? So this is only pretty small. So then, of course, this is better. Of course, if you intuitively, there might be even better one like this. And so this would be better because then you have a distance longer. So this margin will be larger on both sides. Right? So this then will be better. So that's what we are trying to find. And support vector machine provides a way to do it. So that's what we're gonna look at now. All right. Okay, so we already talked about this last time. So we just go to the support vector machine. All right. So why do we call, first of all, why do we call it support vector machine? So so this name has two things we need to explain. So one is a support vector, the other one is machine. So machine here is just an algorithm. Okay, step-by-step mechanism. So we can call it an algorithm. Since there is no electronics or mechanics involved, so we call it machine. We could call it algorithm, or we can also look at it as a machine, just like Turing machine, right? So that is just some kind of device, right? So that does something. So that is a step-by-step. So you have a step-by-step introduction to manipulate inputs. So that its algorithm is also a machine. So now we know that this is a machine, not really. You have some kind of a physical device that would do that does that, right? So it is an algorithm. And then support vector is actually the points on the boundaries of a cluster. So if you going back here, then this will be your support vector. Okay, so this will be on the boundaries, and that's called support vector. So then to come up with this linear separation, we are looking at the support vectors, and that's why it's called support vector machine. Okay, so then what we are trying to do, as we said, that we want to try to find the maximum margin hyperplane. Okay, so it's on a two-dimensional space, this is 9. On a high-dimensional space, there's a hyperplane, but of course, it's a subspace of the space that those data points are in. Okay, so that's what we do on the label data, of course, on a label data set. So if you have a label data set, I want to find a subplane to separate this label data set such that their margins from the support vectors would be as large as possible, because that's a better separation. And the reason for finding such separation is to make your classifying an unseen object easier, because the larger the margin, then it would be clearly, right? It's easier to classify an unseen document. So now let's say we have a training data. So we have x1, y1, x2, y2, up to xn, yn. So this n is the number of training data you have. Okay, so this n for support vector machine doesn't need to be big. Okay, so it could be range from a few tens to a few hundreds, right? So those are good enough for support vector machine training. Of course, the more the better, obviously. And it's a 9 training neural network model. You need a huge amount of training data. So support vector machine doesn't need that kind of thing. And each of these yi is a label. As we said, we use -1 to indicate it is negative and +1 to indicate it is positive. Because we are doing it, we are classifying these data points into 2 classes, particularly, of course, as we said last time, in medicine. All these tests are designed to test whether a particular person has something. If you do, that indicates some kind of disease. If you don't have, that means you are, at least you don't have that kind of disease the doctor is suspecting. So hence, as a positive and negative. So in a medical test, you want a negative result because that indicates that you don't have that thing. The doctor is trying to see whether you have it. So that means you don't have that, right? So but again, so this is used quite a bit. SVM is heavy, I should say, heavily used in medical studies. Okay, so that's what we have. So this is, we need to have this label. And then what is a hyperplane? So hyperplane would be you have a matrix. I'm sorry, you have a vector because we want a linear. So we want a linear, so you have a vector, we call it W. So any, so let me write it this way. So any linear or hyperplane. So let me just say hyperplane is, let's say I have, so each X, I have, let's say, so I'm not going to use N. So let's say I have M dimension. So then a linear, a hyperplane just means that you have coefficient, let's call it W1 for X1 plus W2 for X2 plus WM times XM. So that is equal to some constant. So let's call it C. So that is a hyperplane. Right. So if M is equal to 2, it's just this. So that's a 9 equation or 9 function. Okay, so then we can write it up as a inner product. So this is a inner product of W, which is W1 up to WM, and then X would be just X1 up to XM, and then we move this C to the left. So that's a minus C, then, or here we use B, sorry, I use B. Using C would be just as good because it indicates it's constant. So you move over, that becomes 0. So that's what we do. So we want what? So what do we need to get? We need to train this W. We need to train W so that the margin of this form from the support vectors is as large as possible. So this W is also called a normal vector, which is perpendicular to the hyperplane. So that is the geometric explanation of this equation. So you want to find a hyperplane. Okay. So then the parameter here, B over the norm of W, which is a Euclidean norm. Euclidean norm is, so you look at a vector, you just look at the lengths. So this is vector, and the length of that vector is the Euclidean norm. So basically, you just look at it. So this is the original point. So the coordinate minus, basically is a coordinate square and plus summation of a coordinate squares and take a square root. All right, so that is the norm. And then B over this thing actually is the offset. So that's the length of the margin. Okay. So that is a good thing to know here. So I have a picture. So let's look at that picture. Okay, so so this part is that's the size of the margin. Okay, and of course, so that's one side, and then you look at the whole gap, right? So this is the whole gap. That's 2 times that. Okay, so then you want this to be the margin to be big. So what do you want? So you want the B is a constant. The W is not. So you want this norm as small as possible, yet this line still separate them. So that of course means that it's the larger one. So that's the goal. All right. So another thing we want to look at here is that the projection of vector B. So what it means here is that, let's say I have two vectors. This is the origin. So this is a vector A, and this is a vector B. So what is a projection of vector B onto A? Of course, you take a perpendicular view on this A. Okay, so then if this one is a projection of B onto A. And how do you compute this part? So obviously, this is a, so if you have an angle here, then it is a cosine similarity. Cosine similarity is really just a dot product. So A dot product, and then normalize it. So this bottom here is a normalization, and then is along A. So that's A. Okay, so that is the how we define a projection, or how you could view a projection using this form. Okay. So then, because we want to maximize the margin, so that really indicates that we want to minimize. So this is the we want to. So it becomes we are solving the following minimization problem using the training data. Okay, so which is, so for each point xi, I have a label. Right, so for each point I have a label, and we know that if yi is greater than 1, I want this to be greater than or equal to yi, and if it's yi is negative, I want this to be less than or equal to negative 1, right? So so we want to minimize this distance. We want to minimize this distance, okay, small as possible. Yet they are still be equal, because you want it to be equal, right? So in other words, if yi is 1, you want it to be equal, so which means I want it to be wt xi minus b equal to 1. But then, of course, our goal here is that we want to minimize this part. Still, it's greater than or equal to 1, because you may not be so lucky to get everything to be 1. So you should allow some error, but I want to minimize that error. So that's, you become, so you want to minimize this 1 such that it's greater than or equal to 1. So that is one view of SVM. So then if a solution does exist, then there is a perfect hyperplane separating the two clusters. So this, so then because you want to minimize it so that you get a maximum margin. So this is completely determined by these vectors. And again, we call them support vectors that lie nearest to it. So that's really just a boundary, right? So then those boundary points are called support vectors. So we already mentioned that. So we put things together, right? So then if a solution doesn't exist, then of course we want to allow some acceptable errors. So then of course we generalize this minimization problem into the following problem. So what we want to do here is that, so first I'm going to look at this fact. So it's supposed to be greater than or equal to 1. So that means that it becomes, so if there is a solution, it's a negative, right? So it's less than or equal to 0. So then, of course, if it is greater than or equal to 1, then I want that possible value. If it's a negative, so which means that if, now this is what we want, is to minimize this. Okay, but then we allow errors. So that means 1 minus this thing is less than or equal to 0. So basically we want to take the average of these things. And if it is greater than 0, that means the error occurs, right? So if this thing is greater than 0, that violates this, okay? So then we take the maximum of it, so which would be some error. So maximum of this indicates the error. Okay, so then because we take all the points, so we just aggregate them, sum them up, take the average, and then we introduce a parameter lambda to indicate trade-off between increasing the margin size and showing the xi lie on the correct side of the margin. So that's what we are introducing. So then we still minimize this. Once again, if there is no error, in other words, it satisfies these things, then we just think of it as a 0. So there is no error, 0 error. Otherwise, if this thing is greater than 0, that means it has error, but I want to minimize it. So far so good, right? So this is not, of course, the first person that came up with this really need to do a lot of thinking, but for us to learn it, so it looks pretty straightforward at this time. Okay, so then, so that formulation is not a big deal, but really how you're going to come up with an algorithm to do it. So it turns out this dot product is a quadratic function. Okay, so any dot product is a quadratic. The things you have here is the one, no, I shouldn't say dot product's quadratic because it's linear, but you introduce a term here. So remember here. So that thing, because W is the variables you want to compute. So this thing is no longer linear because you take the norm. So that's no longer linear, no matter what norm you're taking. So then this part becomes quadratic. So then it relies on quadratic programming. And fortunately, so this now has a tangent. So the quadratic programming can be solved. So in algorithm class, we look at linear programming. We use a simplex algorithm there. But then for quadratic programming, we can also do the same. So remember at that, and there, when we try to come up with a optimal solution, sometimes it helps to look at a dual problem of the primal. So this is sort of similar to the linear programming approach, even though it is a quadratic programming because of that distance that we need to look at, right? So because of this. So that is, so this, it would just be W1 square plus WM square, right? So that is quadratic. All right, so then, so the people try to come up with a way to do that computation, right? How do you solve that minimization problem? So they look at the primal So now they introduce a variable, and that so that now the minimization becomes this. Okay, so we look at this quadratic term. And the constraint is this has to be greater than or equal to 1 minus this thing. So this then just becomes a, it is a variable, depends on W, right? But then I want to, so this W are variables, right? So, and then I just want to make sure all of these are greater than or equal to 0. Because the maximum 0 of this, so this is always greater than or equal to 0. So what is the dual? The dual will turn minimization to maximization. So this is the dual. Now, don't worry about how this is derived. So we just take it as granted. Okay, so that becomes a dual. So these subject, okay, the constraints will be summation of Ci times Yi is equal to 0, and Ci is between 0 and less than or equal to this. It turns out that this form, that it's easier to solve, okay, by quadratic programming. Okay, so that takes care of how this can be computed. Okay, so this is a further explanation, so we don't have to worry about. So we just take it and granted. So now you don't have to do it by hand, right? So we do SVM. There's a lot of tools available to carry out that optimization steps. Okay, so that is a linear SVM. Now remember, one of the important assumptions we made is that first, okay, let's go back here. Let's go back here. We say that if a solution exists, that means that if your data points can be separated by a hyperplane, so that means the solution exists to this. Okay. Then we can, so by minimizing this W, we can find a hyperplane that separates the two clusters with the largest margin available. But then this may not always be the case. So if you assume they are all almost separable by a hyperplane, so that means you allow some sub-errors, then you can still do this. However, this may not always be the case. In other words, no matter how you're going to do, at some situations, no matter how you're going to try to find a hyperplane to do this. So in other words, to try to solve this problem, you're not going to come up with a good solutions. So let's see why this would be the case. And then we are looking at why we need to use a kernel trick. Now, SVM is linear classifier at this time, okay? So first thing we need to know is a linear classifier, and solving this optimization, minimization problem is equivalent to solving a quadratic programming. And we find, it turns out that solving its dual is easier using quadratic programming. So that's under the assumption that your data points are separable or almost separable by hyperplane. So remember that. But then it may not be always the case. Then we have to use kernel trick. So before we talk about this, this looks like a busy slide. So before we talk about this, let's just look at an example so that you have some idea why we are doing it. Okay, so this is an example. Suppose according to features of each data points, these points, the red triangles belong to the same cluster, positive, right? So, and these blue circles belong to the negative. Okay, so that's another cluster. So as you can see, no matter how you try to find a line to separate them, you're not going to be successful. Meaning the minimization or the dual, the maximization dual, it has no solution. So because there is no such thing you can do. So how do we do this? So then they come up with a very clever way. So they try to raise certain points to a higher dimension. Okay, so under higher dimension, then it becomes separable. For instance, you imagine this is on a surface. So this is on a surface. So if you somehow you can lift these red, so if we can lift these red triangles up, then if you look at a projection on this third dimension, so this is on a third dimension, then it looks like this. All the blue points still stay here or approximately here. So these are still blue. But then the red ones, maybe now it's up there on this projection, right? So so this is on the view of the third dimension. So that's how you're going to see it. Then of course you see, I can separate them using Z is whatever of this variable, right? So this constant, so we can separate them. So this is a linear separation. Once you are able to somehow lift them up, so that to make this lifting happen is called kernel trick. Okay, so let's look at a viewpoint. Right? So this is really from this is third dimensional, we call it Z. We're going to see this. So you can then, even though when you look at this view, right? So if you from the top you look them down, so there is no way to separate them. So that's just like this. So there is no way to separate them. But because I managed to to raise these dimensions, is somehow now on this particular point of view, right? So then I can separate them. So that is Z is equal to maybe whatever that. If this is C, this is C. So it's a plane, it separates these points. Okay, so then if you look at the projection down, okay, so if you look at the projection on an XY plane, okay, then it becomes like there is a, depending on what function you are using, right? If you're using a circle, then you're going to see a circle. If you use a different kind of function, they use different kind of shape, but they separate them. So it's no longer a straight line, but it is still a curve, right? So here the kernel function is a sphere. So that's why when you look down, it's a circle on a plane. Okay, so now to make this clear, let's see a demo I found from YouTube video, which is pretty good. So let's just look at it. So this is on the plane, so it's not so clear. So these are blue ones, and there's some black ones, right? So these blue ones are supposed to belong to one cluster, and these black ones are the the different ones. So these are training data, maybe represent some kind of disease or some kind of other things. So we want to separate them. And here, obviously, you can't, on this plane, you have no way to separate them using a plane, using a 9, right? So as you can see here now, on this circle, there's still some black dots there, right? But most of them are blue, but this is sort of like what you really want to have. But on this plane, you cannot do it. Now, if I somehow raise these things on a sphere, then I can separate them. Okay, so this is part of the sphere. Well, they are using, this is not really a sphere. This looks like something a different shape, but when you do a projection on the plane back, so this is still a circle. Okay, so now, as you can see, once you raise them up, it is possible to separate them. When you're going back to the two-dimensional space, then it looks like a circle. Okay, so that is the kernel trick can do. Let me go back to where do I? Sometimes I don't know how to operate these things. Let's pick this. Oops. Going back. Yeah. So zoom needs to be improved, right? So this is not good. It doesn't go back to the. So now let's look at what is a kernel trick. Okay, so we can use a kernel trick to avoid explicit mapping, because we know that we can do a mapping, but then we just want to do it automatically. So we try to avoid explicit mapping by hand to get SVM to learn a nonlinear function, okay, of decision boundary. Now, the SVM itself is linear classifier, so that made no mistake on that. But once you lift up the dimensions, right? So then a linear on the higher dimension, when you make a projection down, then it becomes linear. I'm sorry. So on a higher dimension, it's linear, but when you make a projection down, it's no longer linear. So that is what kernel trick can do to us. So we don't have to specifically say what this kernel. So kernel is a function we mentioned. It is a transform, right? So you can try different kernels to see which one is better. Okay, so now let's just look at what this kernel is. So let's say I have these vectors on an input space. Let's call it U. So xi, sj. So kernel is a function. Okay, so that can be expressed as an inner product in another space V. So in other words, we are going to look at a kernel product of two vectors of your current space, and that. So there's a kernel just a map. Okay, it's just a mapping. Map these two vectors into a inner product of another space. Okay, so that is called a kernel trick. And then such a function is called a kernel, okay, or a kernel function. So here it really just, this kernel really means by adding weight. So this is a weight function. So denoting a weighting function for the weighted sum of integral. So that's what a kernel is. So the easiest way to do it is I figured out some kind of mapping here and take a, so this mapping still maps a vector of your current space to a vector in another space, and then we take a inner product. So that is a kernel function we use often. So once we have this, then we can simply replace every product in SVM with a nonlinear kernel function. So we have a linear product, right? We have a products in your SVM optimization problem. Then we are going to replace those with this kernel function. So now here is some common kernels. One is the polynomials, it's homogeneous. Okay, so which means that there is no constant. So we just do xi product yj and take a d's power, or you have adding a constant factor, or there are some others. So when you use SVM with a data set, of course, obviously you will try to start from the easiest kernel first. If the result is good, you stop there. Otherwise, you try different kernels in order to find this hyperplane. The example we looked at earlier, that kernel, okay, so this is the kernel. Okay, z is equal to x squared plus y squared is the kernel function. So that is a polynomial. This is the homogeneous polynomial, right? So there is no other constant here, no constant. So it's a homogeneous polynomial. Then what we are replacing, so for any product in our SVM, we are going to replace the corresponding dimension with this kernel. For instance, if I say this A is AX, AY, AZ, now I raise it to one more dimension. So I have AZ available. And B is the same, BX, BY, BZ. So then what we are doing here is that the product, the inner product, now this is a new space, right? So this is a new space. So the inner product will be AX, BX plus AY, BY plus AZ, BZ. So then this Z under this kernel, this AZ should be equal to AX squared plus AY squared. And BZ here is BX squared plus BY squared. So we're going to replace this part by its kernel function. So that's what we have this term. So that's it. We replace this into its optimization dual and then plug it into a quadratic programming. And then we still, then we are going to get it. So that means since we are solving a quadratic programming, obviously, you probably want to make sure your new thing is still a quadratic. Otherwise, you got to solve a more difficult maximization problem. You wanna keep it quadratic. So this is sphere. Sorry, so this is a sphere. Will be a better way to do this. Okay, so that's kernel trick. So that's it. So that's a support vector machines. So when you have a when you have a labeled data set, you want the SVM to come up with a binary classifier using a hyperplane, then you need to try different kernel functions, right? And then you test it out using the label data to see which one is better. So how do you evaluate them, right? So then the question is, how do I know which one is better? Well, you can always use the same thing we talk about. You look at the precision, you look at the recall, and ultimately you look at F1 score, right? So under this kernel, I have a higher F1 score, and that will be the ones I'm going to choose. Okay, so then how we are going to use our label data to train a SVM model. So this is the common way to do it, or even this is a common way, right? So for the for KNN, you don't need this because they are lazy learner. And for naive Bayes, you can also follow this. So which means I'm going to split my data, my label data into 3 parts. So the larger part is for training. Training means you figure out the parameters, right? For SVM, so this is to figure out this W. Okay, so we are using 80% of the data to train this W. And then we're going to use 10% for development. So development means that we're going to use them to fine tune this. And finally, we use 10% to do testing. Testing means that we'll treat this 10% of data. So it has nothing to do with the algorithm. So the has nothing to do with how you're going to come up with that model. Once that model comes up, then you're going to use this 10% data to test its accuracy, and then this testing will come up with this F1 score. So that's how you're going to. That's how is in general this training and evaluation is done. And there's another way, which is called cross-validation. Okay, and so cross-validation just means that I'm going to split the corpus into n partitions. So corpus just means that your label data into n parts. In each round, one part is selected as the testing set, and the remaining this n minus 1 parts are used for training. Okay, so for instance, you got my data set. I'm gonna divide them randomly, right, into several parts, and then I'm going to take this part out as testing, and I'm going to use the other ones as training. So that is one round, and then I'm going to use this as testing, and then these part will be training. So I get F1 score from the earlier training, and then here I get another score from this training. So ultimately, we're going to get several such things, and we take the average. Right? So we get n4. So that's why we have n4. So we run this for n times because you are dividing them into n partitions. So each partition is used as a testing. The rest is training. So you can run this for n times. So that's called n4 cross-validation. So then you take the average of this F1 score to be F1 score of this cross validation. So the reason why this is done is just try to balance out these data points. Okay, so so try to avoid either overfitting or underfitting by averaging them out. So this is another common methods people used. And there's another concept called baseline accuracy. So it is the some kind of a minimum score. So some kind of a goal I need to beat up, right? So this is a minimum score to beat when using your classifier. So let's say somebody already came up with some classifier, they have some F1 score. So now you're saying that your classifier is better. Then of course you have to use that someone's classifier as baseline because I want to show that this algorithm is superior to the other one. So that it's baseline, or your baseline would come up with some kind of an intuition, right? So, so that you want to beat that one up also. So that's usually how this story is going to end when you use this label data to train a classifier. So with this, I am concluding this module of classification. Classification, of course, has more, because there are more advanced topics than SVM now. Okay, so in particular, we have these neural network classifiers. They tend to be more accurate in terms of classification results, but on the other hand, neural network classifiers need more training data. So we're going to stop here, but I'm just going to say that we have this neural net classifiers such as CNN, convolutional neural networks. So that is the standard neural net classifier. So we are not going to talk about that here, so we stop, but I just mentioned that there are more advanced classifiers available. Okay, so I have 15 minutes left, so we can actually start a new module. Now, before I do that, do you have any question for me? Okay. So now we can look at topic 10. This is topic analysis. So now we are coming back to text data. So SVM, KNN, if base can be used to classify any data points, any data sets. Okay. But for text mining, of course, we want to use these tools to find out the topics of the underlying document, text document. So that's called topic analysis. Some people call it topic modeling, but they just mean the same thing. Okay. So let's see what we are trying to do here. All right, so sitting here in the middle is a text data. So think of a text data as a corpus of documents. So you have a collection of documents. And later on, we can also just look at single documents. So we have a collection of documents and we want to put a label on each document according to their topics. Okay, so let's say we have identify K topics, right? So sports, politics, entertainment, right? So those are topic, travel, automobile, medicine, science, right? So those you can put a label on the document inside a corpus. Likewise, if you are given a document, you want to say what this document is about and how many topics this document involves by putting a label on each document. Maybe a document talks about computer, and then it also talks about application in a certain domain, right? In medicine, for instance, then you will have computer and medicine. So those are the topics of this document. So it's a different from clustering of text document. When you do clustering, we know that we have algorithms to do that. At that time, we don't have a label for each of the cluster. But right now we want to put a label. So that's called a topic for a text data. A label is a topic. Okay, so maybe you can think of this in that way. All right, so we have a text data. So we want to produce several topics. So sometimes we also have some kind of long text data, such as the context, time, location. So where these documents produced, and then also some of when it was produced. So this is not inside the text document, but this is sort of, we call it, sometimes we call them out of band data. So it's not here, but there's some other knowledge. So maybe you want to combine those and come up with topics. And these topics then can be used. So they are sort of like an actionable knowledge now. So that then can be used to go back to your real world, how you're going to apply them. Right, so you may determine to further read them, or maybe you want to, if it's certain things about politics, so you may have something you need to add on. Right? So some kind of recommendations or policies, and then you can add on those. So that is the topic mining is about, or text. I'm sorry, the topic analysis or topic modeling. Or sometimes we call it topic mining, is about. So now let's look at the task of topic mining. So we talk about what it's about and then how, so what is it doing? So what it's doing is I have this text data set and I want to label each document. Okay, and these labels, sometimes you may, now look at this picture here. So where I have N documents, I have say K labels, and according to their either some kind of a measure of each topic, either you look at how many words are in this topic or some kind of probability distribution. So you come up with this, right? Document one has more on topic one, less on topic two, and even less on topic K, but document two has more on the topic two, nothing on topic one, and much less on topic K. Topic N has more on topic K, less on topic two, nothing on topic one. So this is a distribution. So this is something we want to find, right? So you have these documents. Each document talks about some topics, right? So it's hard to find a document to talk about only one topic. Usually you have some other topics, but then their distribution are different. So that's what we want to find out and put a correct label to it. So as we said, when we study these things, we have generative model. Generative model means that we want to come up with a distribution. So let's look at this generative modeling. So input here is a collection of n text documents. So which means now I have this text document, n text documents at hand. And the input also tells me that we want to create k topics. And these k topics are predetermined from your training data. Like this has to be label data, right? So you have a training data set, and then they have k labels on it. So then that's number of topics, right? You have, let's say you have data, you have a collection of documents, and some of them are labeled politics, some of them are labeled military, some of them are labeled sports, some others economy or medicine or whatever. So those are in your training data. And then you look at how many topics they are talking about, that's K. So this is your labeled data. So this is your labeled data. So it's a given. Our goal, ultimate goal, is to learn this, to develop a model by learning this label data so that I can put a correct label, or more or less correct label, on an unseen document. So in the future, then you come up with a new document, then I want to know what this document it talks about. By using this model I learned, I trained by learning this label data. So then that the output of this then would be k topics. So then each of these topics has a distribution. So that is a probability of a DI, which is a document covering topic, say that J. Okay, so that's PIJ. So that means really we want to know for each document what topic, the underlying topic distribution of this document involves. Of course, since this is distribution, so you add them up, that's equal to 1 for each document I. So this document I, you are supposed to have a distribution on k topics. Some of them may be 0, but no matter what it is, when you sum them up, should be equal to 1. So that's what we want to find. And then there are quite a bit of methods that people have come up with. So we're going to spend some time to maybe a longer time to look at all of these methods. Okay, so that is really a fascinating thing to look at this generative model. And then, of course, we are going to tie into text modeling. How do we come up with a label for a document or set of labels? All right. So as anything else, we always start with the easiest one. So I mean, so that we can lay our hands on to begin with, because any complicated things start from not so complicated thing, right? So we know now these algorithms are fairly complicated, but it has to start from somewhere that's not complicated. So that's what we are going to look at. So the easiest thing, right? So this can be, once you know how to use Python text library to process data, you don't have to write lots of code to process data, then you can do this as a CS102 project, right? Computing tool project, in other words. But at UMass Law, computing tool is using C, so you don't have a good library for handling text. So let's say we are doing Python in computing tool. So this is a computing tool problem. Okay, so pretty straightforward thing. And so we have this text data. And then let's say I have K topics, identify sports, travel, and science. So what we're going to do is just look at terms. So how many terms that can be classified as terms used to describe sports? How many terms in your document that can be used to describe travel? Likewise, how many terms that can be used to describe science? Then you can do a maximum likelihood, boom, there you come up with a topic distribution. So it's pretty straightforward. So in other words, the things we learned earlier to use maximum likelihood estimation, then we can use. So this is actually a pretty rough topic modeling, but it's easier to do. Okay, so we do a maximum likelihood estimation, right? So here we just look at the words itself. We have a K topics, we identify K keywords for each topic. So in other words, this topic as terms means that I will just look for a specific word, sports, for this topic, sports, travel for this topic, travel, and science for this topic, science. So there's some similar words for sports, I just ignore them, right? I just look for sports, travel, and science. So that makes it easier, so you don't have to say, oh, whether this word is really related to sports or travel, right? Sometimes you can imagine there is always some kind of ambiguity there, but now we're just saying, okay, we just look at these words. So then sports here appears 4 times, travel appears 2 times, and science appears 1 time. So we can use this maximum likelihood to come up with a count. Okay, so then the slightly different from the slightly different from the maximum likelihood there is that you take each word as an individual input. So here we take each topic. So in other words, we only focus on these K keywords. So that means our normalizer, we only look at these K keywords. So all together, you sum them up. So that will be your normalizer. And then, of course, you do this thing, then of course you sum them up, is still equal to 1. So that is a distribution for these set of keywords. Well, time is up. It's a good time to stop here. Do you have any question for me?
No question. Thank you.
Okay. All right, then that's today's Wednesday. Let's meet again next Monday. So bye-bye now.